Hello friends, welcome to Maths Practice. This is a one-shot video on relations and functions and it covers the entire topic from class 11. So watch the video till the end. First, some definitions. An ordered pair is a pair of elements grouped together in a particular order. Cartesian product of sets A and B is defined as A cross B and it is given by A cross B, which is a set of all the ordered pairs of the type AB where A belongs to A and B belongs to set B. Now remember, order is important in the ordered pairs. That means AB will not be same as BA. And suppose if AB and XY are same, then obviously A is equal to X and B is equal to Y. If number of elements in A is P, number of elements in B is Q, then number of elements in A cross B, it is a set of all ordered pairs, it will be P into Q. A cross the null set will always be null set, obvious. In general, A cross B will not be equal to B cross A always. If A and B are non-empty sets and either A or B is an infinite set, then A cross B is also infinite. If A and B have two elements each, then for example, if A and B have two elements, A cross B will have 2 into 2, which is 4 elements. And A cross B will have how many subsets? We know that the number of subsets is given by 2 raised to n. So A cross B has 4 elements, so A cross B will have 2 raised to 4 or 16 subsets. If you have three same sets A and A, then the Cartesian product A cross A is given by set of ordered triplets A, B and C such that A, B and C belong to A. In this chapter, examples are important, so we'll do different type of examples. First example, if G has elements 7, 8, H has elements 5, 4 and 2, then find G cross H and H cross G. Now you know that if you are having sets P and Q, then the Cartesian product P cross Q has ordered pairs of the type PQ. So G cross H, first element you have to take from G. When you take 7 from G, from H you have which possibilities? 7, 5, 7, 4 and 7, 2. Same way 8, 5, 8, 4 and 8, 2. Similarly S cross G. Second example, if x by 3 plus 1, y minus 2 by 3, this is ordered pair. This ordered pair is equal to 5 by 3, 1 by 3. Find x and y. We have just seen that if two ordered pairs are equal, then you have to equate the elements. So x by 3 plus 1 is equal to 5 by 3 and y minus 2 by 3 is 1 by 3. Solving them, we get x is equal to 2 and y is equal to 1. Example 3. Let A have elements 1, 2, B 1, 2, 3, 4, C has 5, 6 and D 5, 6, 7, 8. You have to verify the following properties. A cross B intersection C is A cross B intersection A cross C. First property. Now to verify this, we first try to simplify the left hand side. B intersection C is null set, you can see that. So obviously left hand side, anything cross null set will always be null set. We know that. So left hand side is null set. Right hand side A cross B will have which elements? 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4. Same way A cross C. So right hand side is A cross B intersection A cross C. But you can see none of the ordered pairs are same in A cross B and A cross C. So their intersection is again null set or void set. So both left hand side and right hand side are null set and hence they are equal. For the second part, to verify A cross C is a subset of B cross D, again we find A cross C and B cross D, and we can see that all the elements of A cross C are in the set B cross D. So A cross C is a subset of B cross D. Now example 4. The Cartesian product A cross A has 9 elements, among which are found minus 1, 0 and 0, 1. Find the set A and the remaining elements of A cross A. So first of all, we know that if the number of elements in A is P and number of elements in B is Q, then A cross B will have P into Q elements. Now here it is A cross A. So number of elements in A cross A will be number of elements in A into number of elements in A. So 9 is equal to number of elements in A into number of elements in A. That means number of elements in A is 3. Now we have two ordered pairs minus 1, 0 and 0, 1. A cross A is a set of ordered pairs A A, where A belongs to A. That means over here both the elements belong to the set A. So -1, 0, similarly 0, 1. All the three elements belong to A. So -1, 0 and 1 are the elements of A. And we already know that A has three elements. That means the set A has elements -1, 0 and 1. Now to find the remaining elements of A cross A, we just have to take the Cartesian product of A with A. So you get all the elements of A cross A. Now we define a relation. A relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product A cross B. The subset is derived by describing a relationship between the first element and the second element of the ordered pairs of A cross B. The second element is called the image of the first element. The set of all first elements of the ordered pairs in a relation R from set A to B is called the domain. That means the set of all first elements is called the domain and the set of all second elements is called the range of the relation R. The whole set B is called the codomain of the relation R. So it is obvious that the range will be a subset of codomain because the range might not have all the elements of the codomain. Let us understand what a relation is. First of all, the relation may be represented algebraically either by roster method or by the set builder method. We know these methods. An arrow diagram is a visual representation of a relation. Now see over here, we consider an example. Suppose the set P has elements X, Y and Z of 3 students and the set Q has 5 subjects, maths, physics, art, biology and chemistry. The Cartesian product of P and Q will have how many ordered pairs? It is 3 into 5. That means it will have 15 ordered pairs. So you can list the Cartesian product P cross Q in the form of ordered pairs. We now obtain a subset of P cross Q by introducing a relation. We want to have a relation, specific relationship between the first element and the second element. So suppose the relation R is the set of all ordered pairs X, Y so that X lies the subject Y. Then suppose if R is given by X maths, that means X likes maths, X likes physics, Y likes art and Z likes biology. Then you can have the visual representation as given below. X likes maths and physics, Y likes art, Z likes biology. And from all the 3 students, nobody likes chemistry. So the total number of relations that can be defined from a set A to a set B is the number of possible subsets of A cross B. Possible relations, total number of possible relations are the number of subsets. That means if number of elements in A is P, number of elements in B is Q, you know A cross B will have P into Q elements. So the total number of possible relations is the total number of subsets. That means 2 raised to PQ. Example 5. Define a relation R on the set n of natural numbers by R is equal to set of all ordered pairs xy such that y is equal to x plus 5 and x is a natural number less than 4. xy belongs to n. Depict this relationship using roster form. Write the domain and range. Now first of all, it is given that x is a natural number less than 4. That means x can take values 1, 2 and 3. So our relation R, in that x will take values 1, 2 and 3. And what will be the corresponding value of y? X plus 5. 1 plus 5, 6, 2 plus 5, 7, 3 plus 5, 8. So our relation R will have the ordered pairs 1, 6, 2, 7, 3, 8. Domain is the set of first elements 1, 2 and 3 and range is the set of the images. That means the second elements 6, 7 and 8. Now from relation we define an important concept called functions. A relation f from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. In other words, a function f is a relation from non-empty set A to a non-empty set B such that the domain of f is A and no two distinct ordered pairs in f have the same first element. So how will you differentiate it? Remember these two important things. Every element of A has one and only one image in B. Like in the diagram shown over here, -1 has one image, 1 also has one image, but that means that on the left hand side means in the set A, every element has an image in the set B. So it is a function. Also, no two distinct ordered pairs in have the same first element. You can see that all the pairs over here mentioned over here, which are the pairs -1, 1, 1, 1, 7, 49 and 525. All of them have distinct first elements. So it is a function. If f is a function from a to b and ab belongs to f, then f of a is equal to b. We write it as f of a is equal to b. B is called the image and a is called the pre-image. The function f from a to b is written as f a arrow b. Now, the following two relations given over here are not functions. Let us see why. If you see the diagram for the first relation, it is not a function because the element 6 has no image. You can see that in the first diagram, in the set A, there are elements 1, 2, 3, 4, 5, 6. From that, 6 does not have any image. So, the first condition is every element of A should have an image in B for being a function. The relation 2 in the second diagram is not a function because the elements in the domain are connected to more than one images. No two ordered pairs should have the first element same, but that is not satisfied over here. You can see that there are many ordered pairs which have the first element same in the second case. So it is also not a function. So whenever you have to find out whether it is a function or not, remember these things, that first thing is in the set A, every element should have an image, and second thing is no two ordered pairs should have the first element same. Now a function which has either R or one of its subset as its range is called a real valued function. Further, if its domain is also either R or a subset of R, it is called a real function. Example 6. Examine if the relations given below are functions or not. If yes, give its domain and range. First one, R is equal to 213142. It is a function because no two distinct ordered pairs have the same first element. All the first elements are different. Domain is 2, 3, 4 first elements and range is the images 1 and 2. Second one, R is equal to 2, 2, 2, 4, 3, 3, 4, 4. Here 2, 2 and 2, 4. There are two ordered pairs which have the same first element. So it is not a function. Third one, R is equal to 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. Yes, it is a function because no two distinct ordered pairs have the same first element. Domain is 1, 2, 3, 4, 5, 6 and range is 2, 3, 4, 5, 6. Fourth one, 2, 1, 5, 1, 8, 1, 11, 1, 14, 1, 17, 1. It is a function because the first element of any of the ordered pairs is not the same. Domain is 2, 5, 8, 11, 14 and 17 and range, all the ordered pairs have the same image which is 1. So the range is 1. Remember, the range is 1 over here because only all the ordered pairs have the same second element. Fifth one, 2, 1, 4, 2, 6, 3, 8, 4, 10, 5, 12, 6, 14, 7. Yes, it is again a function and the domain is 2, 4, 6, 8, 10, 12, 14 and range is 1, 2, 3, 4, 5, 6, 7. Last one, 1, 3, 1, 5, 2, 5. It is not a function because 1, 3 and 1, 5, there are two ordered pairs which have the same first element. We need to understand some types of functions and their graphs. First one, identity function. Let R be a set of real numbers. Define the real valued function f from R to R by y is equal to fx is equal to x. That means the image for all the x is x itself. Fx is equal to x. That is the identity function. Such a function is called the identity function. Here the domain and range of f are R. The graph is a straight line and it passes to the origin. It is very clear because when fx is equal to x, or you can say y is equal to x, means 1, 1, 2, 2, minus 1, minus 1. These type of points will be there. So it will be a straight line and it will pass through the origin. Next is the constant function. Define the function f which is from R to R by y is equal to fx is equal to c, where x belongs to R and c is a constant. Here domain of f is R and the range will be c. Why? Because for each x the mapping will be, the image will always be c, the constant c. So the range will just consist of C. For example, here the graph is of fx is equal to 3. That means for any x, the value of fx or y will always be 3. So it will be a line parallel to the x-axis, and the example is given over here. Third one is the polynomial function. A function f which is from R to R is said to be a polynomial function if for each x in R, y is equal to fx is equal to a polynomial a0 plus a1x plus a2x square plus an x raised to n, where n is any non-negative integer and a0, a1, an belong to R. For example, suppose if I have fx is equal to x square plus 5x plus 6, it is a quadratic polynomial. Now suppose if you are having a function h which is defined by hx is equal to x raised to 3 by 2 plus 6. It is not a polynomial function. Why? Because here n is not a non-negative integer. It should be an integer. So it is not a polynomial function. Here the graphs are given for the constant function. We have just seen linear function means it will be a line. Quadratic means it will have two roots, so it will intersect the x-axis at 2 points. Cubic function, quartic function of degree 4 and quintic function of degree 5. Fourth one are the rational functions. They are the functions of the type fx by gx, where fx and gx are polynomials and gx is not equal to 0. So for example, define the real valued function f which is from r minus 0 to r defined by fx is equal to 1 upon x. So it is of the type fx by gx. And obviously x cannot be 0, so x belongs to r minus 0. Now if you take some points and plot the graph, it will look as given over here. So this is an example of rational function. Next is the modulus function. The function f from r to r is defined by fx is equal to mod x for each x belongs to r. That means fx is equal to minus x if x is less than 0 and fx is equal to x if x greater than or equal to 0. That means for each non-negative value of x, fx is equal to x, and for negative values of x, fx is the negative of the x value. That means actually your fx can never be negative. So if it is 1, then f of 1 will be 1. If it is 2, f of 2 will be 2. But f of minus 1 will be also 1 and f of minus 2 will also be 2. The signum function, it is a function f from r to r and defined as signum of x is equal to minus 1 if x is less than 0, is equal to 0 if x is equal to 0, and if is equal to 1 if x is greater than 1. So it can take only three values, minus 1, 0 or 1. So if you see the graph, it will look in this manner. The domain of signum function is obviously r and the range will be just the 3 points minus 1, 0 and 1. Next important function is the greatest integer function. The greatest integer function f from r to r is defined by fx is equal to square bracket x belongs to r, assumes the value of the greatest integer less than or equal to x. Greatest integer less than or equal to x. For example, if x is between 0 and 1, for example say x is half, then which is the greatest integer which is less than or equal to half? It is 0. So it will give the value 0. Same way if x is between 1 and 2, for example x is 1 and half, then which is the greatest integer less than or equal to x? It is 1. So it will give the value 1. If suppose x is between minus 1 and 0, say x is minus 0.5, then which is the greatest integer less than or equal to minus 0.5? It is minus 1. So it will give the value minus 1. Algebra of real functions. First thing is addition of two real functions. If f is a function from x to r, g is a function from x to r, where x belongs to r, then we define f plus g from x to r by f plus g of x is equal to fx plus gx. Similarly, for subtraction of real functions, f minus g of x is equal to fx minus gx for all x belongs to x. Multiplication by a scalar. If f is a function from x to r, let f be a function from x to r which is real valued function, and alpha is any scalar, means any real number, then the product is a function alpha f from x to r given by alpha f of x is equal to alpha into f of x. Multiplication of two real functions. If f and g are two real functions from x to r, then f into g is a real function from x to r given by fg of x is equal to fx into gx for all x. And this is called pointwise multiplication. Quotient of two real functions, let f and g be two real functions from x to r. The quotient of f by g, it is denoted by f upon g and defined as f by g of x is equal to fx upon gx provided gx is not equal to 0. Next important example, find the domain and range of the following real function. First one, fx is equal to minus mod x. Over here fx is defined for all x belongs to r. So the domain of f is r. It can take any value from r. The range of fx is equal to minus mod x will be all real numbers except positive real numbers. Why? Because whichever number you take, fx will be negative. So the range will be minus infinity to open interval minus infinity to close interval 0. Second one, fx is equal to root of 9 minus x square. Now here it is defined for all real numbers that are greater than or equal to minus 3 and less than or equal to 3. Why? Because when you take a root of a number, that number should be greater than or equal to 0. 9 minus x square greater than or equal to 0. 9 greater than or equal to x square means x square less than or equal to 9. That means the value of x should be between minus 3 and 3. So the domain of fx is minus 3 to 3 close interval. For the range, now x belongs to minus 3 to 3. So the value of fx can be any value between 0 and 3. For example, if you take x as minus 3 or 3, the value of the function will be 9 minus 9, 0. If you take x is equal to 0, then it will be 3. So the range of fx will be close interval 0 to 3. Next important example, find the range of each of the following functions. F is a function given by set of ordered pairs of the type x, x square upon 1 plus x square. X belongs to R. Now we know that x square will always be greater than or equal to 0 and 1 plus x square will always be greater than x square. So x square upon 1 plus x square will always be less than 1. So the range will consist of close interval 0 to open interval 1. Second one, if A consists of elements 9, 10, 11, 12, 13 and f is a function from a to n such that f of n is the highest prime factor of n. Now the highest prime factors of 9, 10, 11, 12 and 13. For 9 the factors can be 1, 3, 9 but the highest prime factor is 3. For 10 the highest prime factor is 5. For 11 it is 11. For 12 the highest prime factor is 3. And for 13 it is 13. So the range will consist of 3, 5, 11 and 13. Next function is fx is equal to 2 minus 3x. X belongs to R and x greater than 0. We have to find the range. Now x greater than 0 is given. So 3x also greater than 0 minus 3x will be then less than 0. So when you add 2 on both of sides, 2 minus 3x will be less than 2. Therefore, the value of 2 minus 3x will always be less than 2. So, the range will be minus infinity to open interval 2. Next one, fx is equal to x square plus 2. X is a real number. X square always greater than or equal to 0. So, x square plus 2 always greater than or equal to 2. So, the range will be close interval 2 to infinity. Next one, fx is equal to x, where x is any real number. So range of f is the whole set of real numbers R. Example 9, the relation f is defined by f of x is equal to x square if x is between 0 and 3, 3x if 3 less than or equal to x less than or equal to 10. And the relation g is defined by gx is equal to x square, 0 less than or equal to x less than or equal to 2 and 3x if 2 less than or equal to x less than or equal to 10. Now over here we have to check whether they are functions or not. For the first one, 0 less than or equal to x less than 3 and fx is given by x square. So now at x is equal to 3, for 0 less than or equal to x less than or equal to 3 it is x square. So at x is equal to 3, fx will be 3 square or 9. Similarly, if we consider the second condition, at x is equal to 3, fx will be 3x, means 3 into 3, 9. So at x is equal to 3, fx is equal to 9, which shows that it has one and only one image at x is equal to 3. Other points it will definitely have only one image, but at x is equal to 3 also it has only one image. So it is a function. Now for the relation G, 0 less than or equal to x less than or equal to 2, it is given by x square. So at x is equal to 2, gx is equal to 4. Now at x is equal to 2, gx is also equal to 3x. So gx is equal to 6 in that case. So for x is equal to 2, the domain of the relation G corresponds to two different images which are 4 and 6. So for one point x, there are two different images 4 and 6. Therefore, it is not a function. Example 10. Find the domain and range of the real function defined by first one fx is equal to root of x minus 1. Now when we take the root, we know that it should always be greater than or equal to 0. So over here x minus 1 should always be greater than or equal to 0. That means x should always be greater than or equal to 1. So the domain is closed interval 1 up to infinity. Now for x greater than or equal to 1, we have x minus 1 greater than or equal to 0. Or we can say fx is equal to root of x minus 1 will always be greater than or equal to 0. So the range will consist of closed interval 0 up to infinity. In the second function, fx is equal to mod of x minus 1. Now over here the domain is the set of all real numbers R, because it can take any value from the set of real numbers R. So domain is R. Now for any x belongs to R, mod of x minus 1 will always be positive. Actually it will always be non-negative, because it is the definition of the mod function that it will always be non-negative. Therefore the range of f is the set of all the non-negative real numbers. Example 11. Let f and g defined from R to R be such that fx is equal to x plus 1 and gx is equal to 2x minus 3. Find f plus g, f minus g and f upon g. By the simple algebra of functions, we have f plus g of x is fx plus gx, so which gives us 3x minus 2. Similarly, f minus g of x is fx minus g of x. That gives us minus x plus 4. F upon g of x is defined where gx is not equal to 0. So f upon g of x is x plus 1 upon 2x minus 3, provided 2x minus 3 is not equal to 0, or in other words x is not equal to 3 by 2. Now from class 11 functions, some questions can be asked in JEE. So let us see these questions. If f, which is from R to R, satisfies the condition f of x plus y is equal to fx plus fy for all xy belongs to R, and if f of 1 is 7, then you have to find summation or sigma R running from 1 to n f of R. Now it is already given to us that f of 1 is 7, and we know by algebra of functions that f of x plus y is f of x plus f of y. So f of 2 can be written as f of 1 plus 1, or f of 1 plus f of 1, which is 7 plus 7, or 14, which can be written as 7 into 2. Similarly, f of 3 is f of 2 plus 1, which is 14 plus 7 is equal to 21, or 7 into 3. So when we take the summation from R running from 1 to n, it will be 7 plus 7 into 2 plus 7 into 3 up till 7 into n. Taking 7 common, we have 7 into 1 plus 2 plus 3 up till n. We know that sigma n or summation of n is n into n plus 1 by 2. Hence, sigma R running from 1 to n f of R is 7n n plus 1 upon 2. This question from class 11 was also asked in JEE. Let us see the question. Find the domain of the function fx is equal to log x plus 3 with the base 2 upon x square plus 3x plus 2. Now we know that by the definition of log function, x plus 3 will always be greater than 0. Correct? Log is defined for all the positive numbers. So x plus 3 should always be greater than 0. That means x should be greater than minus 3. Now For the denominator, x square plus 3x plus 2 should always be not equal to 0. Then only the function can be defined. So x square plus 3x plus 2, when it is simplified, we get x plus 1 into x plus 2 not equal to 0. That means x should not be equal to minus 1 minus 2. So basically the domain will be such that x should be greater than minus 3 and x should not be equal to minus 1 and minus 2. So the domain is minus 3 to infinity minus the two values minus 1 and minus 2. Next question, this was also asked in JEE. Let fx is equal to 1 upon root of mod x minus x. You have to find the domain of fx from the given options. Now we know that under the root you have mod x minus x, so that should always be greater than 0. Mod x minus x should be greater than 0 means mod x should be greater than x. When will the mod value of x be greater than x? Only when x is less than 0. For example, say x is minus 3. Then the value mod minus 3 is 3. So in this case 3 is greater than minus 3, that means mod x is greater than x. So only when x is less than 0 mod x will be greater than x. So the domain will be minus infinity to 0. Functions is a very important topic in maths. So hope the concept of the chapter is clear. This will be extended in class 12th also. Please do like and share the video and subscribe to the channel. Thank you.